Linear equations is what we have already discussed in case of polynomials in the previous session. A linear polynomial is a polynomial with degree 1, and if I have one variable, we call it as a linear polynomial in one variable. If I have two variables, then we call that as a linear polynomial in two variables. Similarly, a linear equation in two variables is an equation which is linear and consists of two variables. Say for example, I take initially with the heading linear equation in two variables. The condition here is that the equation must be linear and must consist of two variables, is what is defined as a linear equation in two variables. Say let's start with, say for example, I take 2x plus 3 equal to 0. An equation which has 2x plus 3 equal to 0 is called a linear equation because the highest power of x is 1, so it must be linear, and then it is a linear equation in one variable because I find only one unknown, which is x. Is an example of a linear equation in one variable, which is x. Is a linear equation in one variable, which is x. Similarly, if I take, say, 2x plus 3y plus 4 equal to 0, then this is called a linear equation because each of its variables have the highest powers as 1. Therefore, it must be a linear equation. But because I have two unknowns, x and y, this particular equation is called linear equation in two variables. So which differs between this and this? This is called linear equation in two variables, x and y. For example, I take x plus 3y square minus 4 equal to 0 is not a linear equation because it is linear in x, but it is not linear in y because the degree of y is 2 or the power of y is 2. So this equation is linear in x but not linear in y. Therefore, on the whole, it is not a linear equation in y because y square defines that y term is not linear. The power of y is 2. Similarly, if I take, say for example, is a linear equation because each of its powers is 1. So this is a linear equation in two variables x and y. So this is how we understand the difference between the linear equation in one variable x and linear equation in two variables x and y, is how we understand the linear equations. Now coming to the general form, how do we represent the linear equation in two variables in general form is very important of this in this topic of the session. So the general form says that a linear equation is always denoted in the form ax plus by plus c equal to 0, where a, b, c are real numbers, where a, b and c belong to R and a, b are not equal to 0, is called a linear equation in two variables x and y, is how we denote in general form. So the linear equation in two variables is ax plus by plus c equal to 0, where a, b, c are real numbers and a or b is not equal to 0. Either a or b is non-zero, is how we define the general form of a linear equation in two variables x and y. Now next, the question comes on how many solutions does a linear equation have? Say for example, if I have a linear equation, I consider the power as 1. Therefore, every linear equation has only one solution. But because the linear equation here is with two variables, now the question comes, if I had a linear equation in one variable as 2x minus 4 equal to 0, then it's easy to find the solutions because immediately I can get 2x equal to 4 implies x 2 times is 2. So x is equal to 2 is the solution for a linear equation in one variable, which we obtain in this form. But how do we find the solution of the linear equations in two variables, which are the two unknowns out there, is what we are going to discuss in the continued session. Now next comes finding the solution of the linear equation in two variables. How do we find the solution of linear equation in two variables is what we're going to discuss here. So for example, let me start with the heading which says solution of linear equations in two variables x and y. Now let me take two referred examples, say x plus y plus 1 equal to 0 and x minus y plus 5 equal to 0. Now these are the two linear equations which I have here. One is x plus y plus 1 equal to 0 and x minus y plus 5 equal to 0. Now the reason why I have taken two linear equations in two variables x and y is that because each linear equation has two unknowns, we need minimum two linear equations for solving to get the solution. Getting the solution out of one linear equation in two variables is not possible because two unknowns, two conditions, three unknowns, three conditions, one unknown, one condition. So because there are two unknowns, I need two conditions out there, the condition 1 and the condition 2, which would yield finding the solution of the linear equations. Now say for example, I take these two linear equations and I wanted to find the solution, then each of them I take separately. X plus y equals minus 1 and x minus y equals minus 5. By taking all the constants to the right and all x and y terms to the left, I would like to solve using the simultaneous method. So once I just arrange all the constants on the right side and all the unknowns on the left, then I try to either add or subtract, so that on adding, we have learned about this in the lower classes. So when we add, this gets cancelled and I get x plus x is 2x minus 6. That implies my x is minus 3, which I get by solving with addition of the two equations. Now once I get the value of x, I can get the value of y either by substituting this x in this equation or this equation, depends on the choice left by you. So when I take x equal to minus 3, in one of the equation I get minus 3 plus y is equal to minus 1, which I have taken out here. This equation, which is considered here, gives me minus 3 plus y is minus 1. That implies y is minus 3 when brought to the right gets 3 minus 1, which is 2. Therefore y is equal to 2. And finally I get the solution. Therefore solution of the given linear equations is x equal to minus 3 and y equal to 2, which are the solutions of the given linear equations in two unknowns x and y, is how we solve algebraically in this method. Now, as we have already discussed that every linear equation can also be represented graphically, so let's understand graphically how we can solve the two linear equations graphically. So the graphical understanding of solution of linear equations is what is for the session. Now let's see how we can find the solution of the linear equations using the graphical method. So the graphical method of finding the solutions is the session topic. Graphical method of finding the solution. Now to find the solution using the graphical method, initially let me take the similar example of the two linear equations in two unknowns x and y. So initially, to start with, x plus y plus 1 equal to 0, and then x minus y plus 5 equal to 0 as two linear equations which I'm going to consider in solving them using the graphical method. Now initially, to start with, as I clearly know that this is a linear equation, then this makes me understand, as we discussed in the polynomial session, that a linear polynomial is a straight line. Therefore, when I graph this on an xy real coordinate system, I get a straight line and I get a straight line, and two lines intersect. That point of intersection is nothing but the solution of the two given linear equations in two unknowns. So graphically, the solution of the two equations is the point of intersection of the two lines, line 1 and line 2. So let's draw the lines and intersect and see where the point of intersection lies. And finally, we get the solution of the given linear equations. So let's start with drawing the line for this, where I just take the table of x and y, and then I find the values for setting this as x equal to 0 and y equal to 0. Then let me find the coordinates of x and y respectively. So when x is 0, I understand this with the corresponding y being equal to 0 plus y plus 1 equal to 0, because x is 0. And then finally, I get y equals minus 1. And similarly, when y is 0, I get x plus 0 plus 1 equal to 0, so that here I get x equals minus 1. So I get each of the points which relate to 0, minus 1 and 0, which when plotted on xy coordinate system and joined with a straight ruler, I get a straight line for this equation. Similarly, I take the table of values for this and then draw the straight line correspondingly for that. So let's see how the table of values would be for the second line. So taking the table with each of x and y, and then with x is 0 and y is 0, I find the corresponding x and y values respectively in the table filled up. So here, when x is 0, I understand that I get the y which is equal to 5. So therefore, when x is 0, my y is 5 as substituted here. And similarly, when my y is 0 equal to 0 implies x is minus 5, which I get out here. So using the two different table values which I have obtained, we are going to find the different points plotted on the straight line. So initially with this, my points are 0, minus 1 and minus 1, 0, which are the points I obtained in case of this. And in case of this, I get the points 0, 5 and minus 5, 0, which are the corresponding points which I obtained for this line. So let's initially draw a straight line joining these 2 points plotted with respective points, and then draw a straight line plotting these 2 points respectively, joining with a ruler. So let's take a real xy coordinate system. This is x-axis and this is y-axis, and this is the origin, and from where I take the straight line with points plotted. Therefore, I take the scaling on x and y-axis with this starting with 1, 2, 3, 4, 5 and 6, etc., and then minus 1, minus 2, minus 3, minus 4, minus 5 and minus 6, etc., And similarly, I get here 1, 2, 3, 4, 5 and 6, etc. And then I get -1, -2, -3, -5, 4, 5, 6, all with minus signs. Then once I get all the scaling done on x and y axis, I first plot the points for the line 1 and then plot the points for the line 2. So initially, to start with these 2 points, 0, -1 lies 0, -1 comes down because these coordinates move along y-axis and these move along x-axis. And -1, 0, so moving here, -1 and 0 comes here, and 0, -1 comes here. When I just intersect them, I get the coordinates. Similarly, I just join the points. And this is a straight line connecting x plus y plus 1 equal to 0 is the equation of this straight line. Similarly, I draw the straight line this using these 2 points, 0, 5 and -5, 0, which intersect Therefore, I get this line to be x minus y plus phi equal to 0. Therefore, these 2 lines intersect at this point, which gives me the point of intersection of the 2 lines. Therefore, the point of intersection as we have obtained in the previous case was 3 and 2, which I got in the case as x 2x equals -6. So x is -3 is what I obtain approximately, because I'm not using the graph paper, so I get the approximation where here the x coordinate will be -3 and my y coordinate will be -3 plus 1, which is 2, which approximately touches here. So this is the point of intersection which I obtain here, and the point of intersection decides the solution of the given linear equations. Therefore, the point of intersection is here P, which is -3, 2. Therefore, this value of x and this value of y will be nothing but the solution of the given linear equations. So for the given 2 linear equations, the x coordinate of the point of intersection, which is -3, and the y coordinate of the point of intersection, which is 2, will be the required solution of the given linear equations, is how we get the solutions. So now that we have connected the graphical method of understanding the solutions of linear equations, both algebraic and graphical method, now this makes me understand finally with my learning outcome that if I find the point of intersection, then the x coordinate of the point of intersection will be the value of x, and the y coordinate of the point of intersection will be the value of y, and which together forms the solution of the given linear equation. Now this makes me understand with different cases of the solutions. Say for example, if the 2 lines do not intersect, then what is the status of the solutions of those 2 lines? If the 2 lines are coincident, then what is the status of the solutions of the equation? If the 2 lines intersect, then what is the status of the solution? So the different cases arise with different types of intersections, as we see in mathematics. To start with case 1, the heading is nature of solutions based on the shapes of the lines as obtained in drawing on the real xy coordinate system. Based on the trend of the lines, we can decide the nature of the solutions, which is a very important concept connecting the straight lines, the trend of straight lines with that of the solution of the linear equations. So nature of solutions starts with case 1, Say for example, if I have two lines L1 and L2 given by A1x plus B1y plus C1 equal to 0, and L2 with A2x plus B2y plus C2 equal to 0 are the two lines intersecting at one point. That implies if two lines intersect at one point, then the solution is unique in case of this kind of a trend of the two lines L1 and L2. So if I have two linear equations in two variables x and y, then we say that the solution is unique if the two lines intersect only at one point. Unique is one and only one solution. That is, we get only one value of x and one value of y in case of this kind of lines intersecting. This being the example of case 1. Similarly, I take the case 2. If I have, say, two lines which are parallel, L1 and L2 given by the similar equations, but if the two lines are parallel, where we denote with L1 parallel to L2, implies the solutions So this implies with the general understanding that the two lines never meet. When two lines are parallel, they never meet, even at infinite distance. That means when two lines do not meet, there is no point of intersection and hence no solution. That implies the two lines L1 and L2 do not intersect and hence have no solution. They do not have solution because they do not meet. No intersection, no solution is how we understand this. Now the next is case 3, where there is a possibility that the line L1 and the line L2 coincide with one over the other. So such lines are called coincident lines, where this is coincident lines. In case of coincident lines, we see that one line passes through another line. That means they both intersect at infinitely many points. They intersect. This implies the two lines intersect at infinitely many points. The lines L1 and L2 are said to be passing through each other infinitely many times, and hence mathematically they are said to be intersecting at every point. Hence they intersect at infinitely many points, and therefore we get infinitely many solutions. One intersection, one solution. No intersection, no solution. Infinitely many intersections, infinitely many solutions is how we understand the nature of solutions connected to this, this, and this. That implies infinitely many solutions is how we understand the nature of solutions connected to the graphs. Cut. Now, if I take the lines in general form and see how we can identify whether the two lines in the general form are intersecting, parallel, or coincident, or with unique solution, or with no solution, or with infinitely many solutions, is what we're going to discuss for the session. Say I take the two lines in general form as in the form of line L1 I take my line L1, which is A1x plus B1y plus C1 equal to 0, and my line L2 is A2x. Say for example, this is A2x plus B2y plus C2 is equal to 0. Then in this case, let's see how the different cases are derived using the coefficients. Generally here, I'm trying to connect the coefficients with nature of solutions. So the coefficients here are A1, B1, C1 for the line L1 and A2, B2, C2 for the line L2, both in linear form with two variables x and y. So let's see how we can connect the coefficients with nature of solutions. Now coming to case 1, I understand if A1 by A2, if I take here, is not equal to B1 by B2, that implies L1 intersects L2, and in turn when L1 intersects L2 I get unique solution. So implies unique solution. You can take many examples where you can verify with A1 and A2 and B1 and B2 and then divide and see. Say for example, I take x plus y plus 1 equal to 0 and x minus y plus 5 equal to 0 are the two lines, then clearly I identify here A1 is 1, B1 is 1 and C1 is 1, and here my A2 is 1, B2 is minus 1 and my C2 is 5. Then I try to simplify A1 by A2, that implies my A1 by A2 is 1 by 1, which is 1, and my B1 by B2 is clearly 1 over minus 1, which on simplification gives me minus 1. So clearly I see that 1 is not equal to 1 minus 1. That implies A1 by A2 is not equal to B1 by B2. And therefore, using the condition of A1 by A2 not equal to B1 by B2, I say that implies the lines L1, which is given by this, and L2 given by this, L1 and L2 intersect at one point and then unique solution exists, is one of the examples through which we can verify the case 1 of understanding this with algebraic approach. Now let's see the case 2 in general form, where the coefficients are connected to identifying the nature of solutions. So coming to the case 2, let's take the condition. The condition says that if A1 by A2 is equal to B1 by B2, which is not equal to C1 by C2, that implies the solution, that implies line L1 is parallel to L2 and they do not have solution. So as we already seen here, the two lines are parallel, then the two lines do not intersect and hence they have no solution. But mathematically we identify algebraically for no solution implies this is the condition which the two lines must satisfy. Let's take an example and see how we can prove the statement. Say for example, I take the two lines L1, which is x plus 2y minus 3 equal to 0, and my line L2, which is 3x plus 6y minus 18 equal to 0. Now these are the two lines which I wanted to prove with the given condition. So let's take, we clearly know that my A1 is 1 and B1 is 2 and my C1 is minus 3, and coming to the second line, my A2 is 3, B2 is 6 and C2 is negative 18. Therefore, when I just substitute in place of this, I get A1 by A2, which is 1 over 3, which is equal to B1 by B2, which is 2 by 6, which on simplification gives me, implies this is identically equal to this. And when I take C1 by C2, this is not equal to minus 3 over minus 18 because this gives me 1 by 6. Therefore, this clearly satisfies the condition A1 by A2 is equal to B1 by B2, but that is not equal to C1 by C2, which gives me 1 by 6. And they give 1 by 3 and 1 by 3. Therefore, this clearly satisfies the condition that A1 by A2 equal to B1 by B2. not equal to C1 by C2. Therefore, I can say that the lines are parallel. That implies these two lines, as given in the example problem, are parallel. That implies no solution. So this decides the factor on identifying whether the two lines are having the solution or not having the solution. So straight away with this condition, I can say the two lines have no solution because the two lines are parallel with this condition.